Hi and welcome to my video series on integration, theoretical integration, so not applications, required for Unit 4 Specialist Mathematics. And this will be video 1, and I'll be rolling through some of the ideas that are covered in the syllabus, and I'll be using the Cambridge textbooks as a guide for the order that I run this in. So you can see the textbook references there and the learning goals and success criteria as required. So let's start with the further integration rules for complex functions topic. And it's going to start with a couple of reminders. So first of all, let's do an example where we talk about how we integrate. And it's a total integration problem, so it's definite integration involves finding the area or the definite integration depending on the context of the question. So when I integrate this, e to the 2x becomes e to the 2x over 2. So don't forget that when we integrate an exponential, it stays as the exponential, but we do have to divide by the integral of the inside function. And that, of course, is only for exponentials that have base e. Any other base, there will be another division factor of log, natural log of that factor. So it might be worth having a look at that again if you're unsure. 2x integrates to give x squared. And if we're doing definite integration, there's many different ways you can write it. I like square brackets, but we are integrating between 2 and 0 for those functions. So then we just substitute in first our upper bound, e to the 2 times 2 over 2 plus 2 squared. Seems like I've got too many 2's in this question. And then I get e to the 2 times 0 over 2 plus 0 squared. Now the polynomial term, as always, when you put 0 in, it just disappears. But be careful you don't assume that with the exponentials terms, because they don't just disappear. So here I get e to the power of 4 over 2 plus 4 minus, and e to the power of 0 is 1, so it becomes minus a half. And that, of course, gives me a half, however you want to write it, half e to the power of 4 plus 3.5, or 7 over 2, or however you want. So there's our answer there. That's a integration reminder and also a definite integration reminder. So let's also recall some of the ideas around the absolute value or modulus function. So if we have these straight lines surrounding a number, it tells us to find the absolute positive value of that number. So the absolute value of 7 is 7. And the absolute value of negative 7 is also 7. So we just basically take a negative number and make it positive. Now the absolute value of a, of negative a, sorry, seems to be a, but we have to be a little bit careful here because it's not necessarily a. If a is greater than 0, greater than or equal to 0, then the absolute value of negative a is equal to a. But if a is less than 0, then the absolute value of negative a is equal to negative a. So just got to be careful about how it works algebraically. And it's going to be really important moving forward that you're always thoughtful about what we know about the number. In part A and B here, we knew the number. Taking the absolute value of a number we know, no problems. But here we had a variable that could be positive or negative to start with. So just be a little bit aware of that. And of course D is just evaluating a sum involving absolute values. This is 3, this is 3, this is 3. So we get 3 plus 3 minus 3 is of course 3. So there's a couple other things that we have to consider. So now the question is, and this does come up in the math methods curriculum, but we don't talk about it in a lot of depth, why does log y equal log x go to dy dx equal 1 over x? It's one of those strange phenomena in mathematics where we sort of get this part, that's kind of like in our line of polynomials. You end up with x to the power negative 1, we treat it like a polynomial when we derive that. So why is it that log sneaks into our little polynomial list here? And let's have a look. Consider if y equals log x, well that means that x is equal to e to the power of y, which means that dx dy is also equal to e to the power of y, because when you derive an exponential you get itself. And we're deriving this with respect to y, so we don't have to worry about multiplying by the derivative of y because we're deriving with respect to y, as you can see here with dy in the denominator of our calculus term there. So this is okay, but the reason why this is in my thoughts, this is very much a specialist concept, is that we're now dealing with a slight variation, and what we're about to do to our calculus term is really a specialist concept, and it sneaks into differential equations later on. What I'm going to do is I'm going to reciprocate it. So that means I'm going to flip it upside down. So if dx dy equals e to the y, then dy dx equals 1 over e to the y. And of course, we know that x equals e to the y. That came in up here. And so therefore, this is just equal to 1 over x, which is exactly what we're trying to prove. That's the mathematical reason why dy dx equals 1 over x when the original function was log x. And it's just pretty much to do with the fact that when you derive an exponential, you get yourself. So this will be important later on, chapter 13, chapter 14 of our work this in unit 4. So let's take this a little bit further. If y equals log x, then dy dx equals 1 over x. We know that. If y equals log negative x, then dy dx equals 1 over negative x. But we have to multiply by the derivative of the inside function of negative x. And so this is equal to 1 over x because the derivative of negative x is just negative 1. So what problem we have here is that when you derive log x and log negative x, we get the same derivative. So what does that mean for our integration? If we integrate 1 over x, well, the answer is actually log x if x is greater than 0, and it's log negative x if x is less than 0. Because we can't do log of a negative number. So if log is negative, like negative 7, well then it suits this function instead. And so we get this. It's a binding of what we've done so far in this video. The integral of 1 over x dx is equal to log of the modulus of x plus c. And the only issue we have left is that x can't equal 0 because we also cannot do log of 0. So that's the only issue we have left. And we brought it together, so that's good news. So, example 3, a couple of reminders. If we integrate 1 over 3x, this of course is equal to log 3x with the modulus sign now, divided by 3, because we have to divide by the derivative of the inside function plus c. So that's, I don't know why I left so much space for that. Let's reduce that space a bit. That's our solution there. And example 4, if we integrate x plus 3 squared over 9x, this question here requires us to recognize that, yes, we are going to head down the path of having a log function in our integral, because that's what this topic's on. But we have to do a little bit first. We have to realize that when we integrate this, x plus 3 squared is x squared plus 6x plus 9. And that's all over 9x with respect to x. And so now it's about realizing that when we integrate this, we can separate the terms. So we get x squared over 9x plus 6x over 9x plus 9 over 9x with respect to x. And that's equal to x over 9 plus 2/3, 6 over 9 is the same as 2/3, plus 1 over x dx. So this is all about recognition of the fact that we have a single term in our denominator and multiple terms in our numerator, so we can change that to a dividing each individual term through. We have bigger problems if we have multiple terms in our denominator, but we will deal with those later in this chapter. So this is fairly trivial now, I hope. This becomes x squared over 18. So we increase the power by 1, divide by the new power, and 9 times 2 is 18. Plus 2x over 3, it's just a number, now it's 2/3 times x, which is 2x over 3, and then plus log the modulus of x, and plus c. So there we have it, and we have a final example, example 5, I believe it's the final example, there we go, and that is to evaluate this integral. And explain the problem with evaluating a second integral. So let's have a quick look at this one. So I'll create a bit of space all over the shop, shall we? So evaluating this integral first of all, hopefully you recognize here that this is simply log, it's 3 log of x plus 1 minus 3 log of x minus 1, and it's between 5 and 4. And now we can just do a substitution in. So we get 3 log of 6 minus 3 log of 4. These are all modulus. And then we substitute in, that's substituting in 5. We subtract from that what we get when you substitute in 4. 3 log of 5 minus 3 log of 3. And now we can simplify this. I'm going to take 3 out as a common factor, and we're left with log 6 minus log 5 minus log 4 plus log 3. So we have negative of a negative on the 3. So we get that as a positive. And that gives us 3, don't ever forget your log laws, 3 log 6 times 3 over 5 times 4. If we subtract, then we divide, and if we multiply, then we if we add, then we multiply. And of course, we don't need the modulus anymore because it's just a number and we know it's positive. So we get 3 log of 18 over 20, which I'm going to say is 9 over 10. So there's our solution, and it's a definite integral, so we don't have to worry about a plus c either. And that's as simple as we can make that without maybe splitting it back up into multiple logs. The problem with this one is that we've got 2 hyperbolic functions in play. We've got 2 asymptotes. So if I sketch this function, you see an asymptote at -1 and an asymptote at 1. And what we've got is a situation where, because we've got a subtraction, we have something that maybe looks like this. And I'm not going to go into too much detail of exactly what it looks like, but maybe it looks like this. In the previous question, we found the definite integral between 4 and 5, and it works, but between 2 and -2 is going to be from here to here. We've got 2 asymptotes in between. So if you're ever integrating a log function or an hyperbolic function which comes out as a log after the integral, just be wary that you might be dealing with a situation where you have an asymptote in your definite integral, in which case it's not really possible. So we've got that issue to deal with. So we can't really do that technically, although we could integrate it and find the definite integral. It wouldn't mean anything in terms of area. So there's our learning. Hopefully you're happy with that, and that's to do with inverse hyperbolic functions to get log functions and modulus functions. All the best.